Want more lights?
What's that?
Are you sure you don't want more light?
I'd really like my display to show up on the screen. That would be a good start. Let's try this again. Our projector stopped. Well, while they're working on that, the first talk I'm supposed to say is what is HamSCI? So my name is Nathaniel Frizzell. My call sign is Whiskey 2, November Alpha Foxtrot, and I'm probably the principal co-founder of HamSCI. And HamSCI is a ham radio science citizen investigation. And the way it got started was I first got into atmospheric physics through ham radio. I just started when I was in 8th grade or so, and I eventually got my license, and I eventually got my PhD in electrical engineering using information data collected by the SuperDART radars. So while I was in grad school, I learned about the reverse speaking network, and I said, oh, these observations of all these CW signals, this looks very similar to what we had to the SuperDART type of observations. I bet there's propagation information in there. And so I started working with that data, and then I met some other people like Magda Moses and Ethan Miller and Greg Earl, and we said, oh, I bet we can make an organization out of this. And so that's where HamSCI came from. So there we go. All right.
Technology.
So these are just some photos from Hamvention and also from the HamSCI meeting. We actually had a full 2-day workshop with a talk similar to this hosted where I work at the New Jersey Institute of Technology. So it's quite a diverse group. Our main objectives are to advance scientific research and understanding through amateur radio activities. So we want to encourage the development of new technologies to support this research. We want to provide educational opportunities for the amateur community and the general public. So we want to both have fun in ham radio and actually produce real science results all the way up to the peer-reviewed refereed journal level, which we are now accomplishing. So we have many people involved. This is an incomplete list of the institutions that participate in these sorts of activities. And this is just also a brief list it's a selected list of some of the presentations that we had at the HamSCI workshop. So it's quite diverse. We have everything from eclipse observations, which I'll be talking about today. There are people who study VLF and low frequency propagation. People are looking at NVIS, people who are doing fine scale frequency and timing measurements. So it's a very diverse group. It's kind of like a collective. So if you are a science-minded person or interested in this sort of thing, you'd like to be involved, one of the best ways to do that is to come see me or one of the students at the HamSCI booth. You can talk to us. And we have a Google group, a discussion group, where we just discuss these ideas and people work on different projects. So today we're going to hear 3 different talks. The first one is going to be from Dr. Phil Erickson from the MIT Haystack Observatory, and he's going to talk about the connection between space physicists and space physics researchers and the ham radio community.
It's already a good day. Slides are on the projector, so very happy to watch here. So I'll ask this.
There's an on switch.
So that's the same thing. Nathaniel are you enjoying the Hamvention? Yes? Great.
Yay.
And we really appreciate you coming to the forum this morning. So my name is Phil Erickson, as Nathaniel mentioned, Whiskey 1 Papa Juliet Echo. And I'm from an observatory in Massachusetts that specializes in radio waves. We do a lot of things, but one of the things that we're doing is trying to bridge the folks in this room who are enthusiastic radio amateurs, who are even more curious than the normal radio amateur, because that's why you're in this room. And I'm presenting this on behalf of my colleague, Dr. Ethan Miller, Killer Wade Golf Uniform, who couldn't make it but sent all of his regards, and so this is a bit of a fusion of what Ethan was going to talk about, what I'm going to talk about. It's actually addressing a comment that we got a lot yesterday. We were over in the Ham Radio 2.0 area, and we had a lot of people wander by and ask the usual questions that you ask of any scientist. Why are you doing this? What kind of interest do I have in it? What do you guys get out of it? Kind of this so what question. And so I'm going to try to answer that a little bit here. Let me start my timer because being an academic, I have to make sure that I'm actually not going to go over time. We're all used to going to meetings where there's a fellow with a hook standing there waiting to pull you off. Okay, so this is some pictures of some of the things that Ethan does. That's his particular station right down here. He lives in Maryland, and he has, hex beams, various wire dipoles, various, fan dipoles, many other things. This object might be familiar to some people in the room who were at CW. And the point is that this is the community that I'm talking to at the moment. You are all extremely enthusiastic about this as a hobby, as I am. And this is where we start. So the question is, how do we bridge from there to the world of scientific research? One of the things that HamSCI has realized in the last couple of years is that I think we've hit a nerve. There is, in fact, a bridge here. And what I'm going to show you in a little bit is that this is, in fact, not a new concept. It's been around for many, many years, as long as the hobby's been active. And I think all of you, by being curious and participating in things that HamSCI will organize and giving back, I think we can make a real contribution to the world of scientific research, in addition to advancing the hobby that we're all enjoying a lot. So why do it? That was one of my questions a moment ago. You're all extremely good observers in order to be able to do your hobby. And we tend to have somewhat above average technical interests and skills. In fact, this community is incredibly deep with people that sometimes in other fields of research have very, very well-honed skills. Anybody who's a PXer in here. Day-to-day propagation and what's open and what's not is the bread and butter, right? That's how I'm going to hear someone, that's how I'm going to hear whether the 3YOC expedition actually got to the way right? Those people who are doing MCOM, NVIS propagation is the way you're going to communicate in a regional area, and so there, once again. And over the years, people in this community are quite resourceful and thrifty. Reverse beacon network is a classic example, something that benefits the hobby, and it turns out that, as Nathaniel mentioned, through peer-reviewed publications, we're figuring out that there's a lot of science. So there's a lot of reasons to do this. My point is this is not new. This is Edwin Howard Armstrong, the fellow who came up with FM, the fellow who came up with the superhead receiver. There he is in his World War I uniform. That is the patent drawing for what ended up being the super regenerative receiver. Here he is, in fact, you'll recognize that same diagram on the board here at Columbia. And there is a article from the February 1920 QST, a new method for the reception of weak signals at shortwave lengths. That's laying out some of the screw gens there. Where did he publish it? He was the president of the Radio Club of America. Where did he publish it? He started publishing it in QST. So this has got a long history. And I promised I wouldn't embarrass Bob Berlinga in the back, so I will. So there is Whiskey Bravo for APR, who developed APRS because, again, he wanted to provide something that was useful, and there's a ton of data in there. Here's Harold Beveridge. Anybody heard of the Beverages? There's Harold sitting at his station, again, inventing things that are useful for not only radio amateurs, but also for professional people who design antennas at low wavelengths. Joe Taylor and Steve Frank, you may have heard of them. Steve Frank actually comes from my ionosphere. He's a professor at Illinois. And Joe, of course, has this thing called the Nobel Prize, but he did this very, very interesting work in weak signal communications, which is basically revolutionizing paths that you thought were not open, even at solar minimum, but in fact are wide open. It comes out of the amateur community because Joe is first and foremost an amateur radio operator, in addition to being a truly outstanding scientist. There's Reginald Fessenden, the guy who invented radio telephony back in 1906, and there he is with gear that for a few generations ago would be familiar. I'm just picking tiny little examples here. This is Buzz Reeves, the guy who was the president of Cinerama, the guy who figured out how to put a magnetic oxide strip on your film so that the sound synchronized with the picture instead of having somebody have it put on a record. cue it, which is what he used to do. He was an amateur. There's February 1922, my friend Bill Wiles pointed out to me. This is QST. This is a transatlantic experiment. There's Paul Godley, ARL Successful Overseas Listener. That's with no S. Overseas Listener. So even back then, individuals were beginning to explore this technique, this territory. And the advantage here is that we have far more fabulous tools, and they're growing every day. But the point is that this community, since day one, has been interested in pulling this kind of information out. And I think we can all do it together. So I'm going to spend maybe a few minutes for those of you who don't have your head down in space physics and the upper atmosphere all day, just to sort of talk about why as a scientist would I be interested in this, coming from the professional perspective. Our planet is surrounded by both a neutral atmosphere and an ionized atmosphere. The neutral atmosphere comes along with the fact that the planet has a rotation, and the rotation velocity plus gravity is keeping a gas near the planet. And it's organized into various things: troposphere, stratosphere, mesosphere, and we're just going up in altitude here. Troposphere, of course, is what we're breathing. But as you get up into the mesosphere and the thermosphere, these are organized by temperature, by the way. You're now getting into altitudes which are actually the domain of the ionosphere. So this neutral gas gets flooded with extreme ultraviolet radiation from our sun, which is a medium-sized reactive star, and then that creates an ionosphere, which is then classified into things like the D region, the E region, F region, which if you pay attention to HS propagation forecasts, you're listening to all the time. Those are rough sort of altitude ranges. Out below that, out beyond that, there's a plasmasphere, which is basically the ball of ionized gas that's kind of stuck to the magnetic field lines and rotates along with the planet turns. And even farther out, there's an area that's just controlled by the magnetic field, called the magnetosphere. And then you can even find plasma, which is what the ionosphere is composed of, all the way out in the interplanetary place between planets and the place between star systems. There is space weather in all of this. So just like a meteorologist down on the ground will first define climate, what's the average temperature today, on average according to the records it's going to be this high and this low, and then the weather is what actually happens when you take off the climate. We are beginning to get climatological models that are okay enough that we can actually take them off and look at space weather, but it becomes very clear that we need a lot more data and a lot more observations, even beyond what the professional networks can provide. And that's where the partnership is really quite useful. So this is just another diagram for those of you who want to organize it by altitude. I mentioned that there's the neutrals, the troposphere, stratosphere, mesosphere. And by the way, as the lighter species are the ones that hang around the longest, and the heavier species hang around closer to Earth, so the weight of the atmosphere gradually gets less as you go up. And by the way, there's the ozone layer in the stratosphere that everyone refers to for reference. And then you finally get to the point, by the way, called the exosphere, where there's so little atmosphere that particles don't even collide with them, they just fly ballistically. And so you need a different way to describe that. But this is the neutral atmosphere, which is the source for the ionosphere because of this extreme ultraviolet radiation from the sun. The extreme ultraviolet is quite weak in energy compared to the stuff that we're seeing outside, but it's highly variable. We don't go outside and say, oh, it must be solar minimum today because it's kind of dark out there. We don't do that because the sun and optical wavelengths moves maybe 0.1% in energy between solar minimum and solar maximum. The ionosphere can vary by 50 to 100% because that extreme ultraviolet part of the solar spectrum is very, very highly variable. So that is the part that in fact creates all of this wonderful structure, which as amateurs we all know varies in 4 dimensions, 3 space dimensions and 1 time dimension. So it's a very interesting picture. And this is what we're studying as professionals, and this is what every time you make a contact with somebody over a long path, short path, what have you, this is influencing how you're doing it. And so these are, I just briefly mentioned, these are some of the names. People have been using different techniques to measure them professionally, and now we're beginning to do it by paying attention to communications links. And that happens to be what the electron density profile will look like if you look just up. That's a log scale there, so 10 to the 6th electrons in a little box ascending your cube. By reference in here, if I grab the cube, it's about 10 to the 20th particles. So this is really thin stuff, but it's not zero. It's not the vacuum of space. Things get complicated. There's your little mass spectrometer there, and there's your little profiles kind of changing. So, you know, it has lots of physics richness. This is a cartoon of the Sun-Earth system, not to scale.
Good.
But we have a magnetic field around us, the plasma coming off there is magnetized, so there's lots of complexity there. Ethan threw this in just to show you that there are reasonably complicated loops in here. But that's what we worry about as scientists, and we need more data to explore them. Just to show you that this is not a uniform thing, you can watch the waves. This is derived off of the Global Positioning System, satellite information, actually. So I'd say that that's a rather complicated picture. And you can just watch it. It varies in space and time. I could spend my whole career in one little box. That's the schematic close-up view of what we're talking about. You see why we're interested in the systems, the physical system. And you're all living in the middle of it and using it every day when you turn on your radio. So my point is, to very briefly to wrap it up, is that there are variations on all time scales, milliseconds to millennia, buried in there. And there are things that occur in little 100-meter chunks, and there are things that occur across kilometers and across continent size. So there's spatial and temporal scales in here that we can all look at, and there's this neutral one that's actually sort of getting in there. The point is, there's a bridge. How is this system coupled together? And this is honestly, Nathaniel can tell you, this is at the forefront of when we go to professional meetings. How do these neutrals and ions couple? We need more data. Rich Moses can give you this copy of the CQ article from 1949, pointing out that amateurs can fill in many gaps for radio wave propagation, so you all have a crucial role to play. And this is one of the reasons. We have absolutely disruptive RF hardware coming out. Yes, that's $7.75 down there for a Silicon Labs SI5351 locked oscillator, which is good enough to do science with. So that gets to be accessible to this community. We can organize ourselves and figure out what we want to measure, and that's part of the HamSCI collective. And by participating here, you get to be part of it. So I'm just going to leave that up. We are in really an exciting discovery period. I think in my career I have not seen this much of an explosion of big data, and the amateur networks are a crucial part of that. If we can, as scientists, help us remember and use what's gone before and figure out what the best tool is for doing science results, we get to leverage everyone's really excellent observation powers here, even far beyond some of my colleagues, actually. And so I think together we can really advance this coupled system, and I'm looking very much forward to doing that with everybody and also pursuing my hobby. So that's just an introduction of why we do
Start putting his computer in, and while he's doing that, you can ask Bill some questions.
Sure, I can take a question or two if anybody has one. Yeah, go ahead.
Have you looked at wall noise, noise and safety, looking information that seems to you primarily against electric propagation?
Right. The idea was there's a nearly 70 or 80 year database on VHF and UHF propagation that are available from dedicated individuals like this. What we're also trying to do in the collective is try to see how we can put all. First, you have to gather the data in a way that's accessible for scientists. And we have Bill Engelke back in the corner here who is attempting with some people in NGIT to also do that. So stay tuned. But yes, it is VHF propagation in the 1950s was the frontier. And in fact, there's a bunch of science studies around the time the space age started, which they understand the growth of VHF. So yes, all of that data is extremely useful.
Okay.
Okay.
Round of applause, please. I'd like to welcome who I think is a familiar face to the ham radio community here. This is, what's that?
Unfortunately,
Angel Vasquez, Whiskey Papa 3 Romeo, from the Arecibo Observatory. And I'd like to note that the Arecibo Observatory actually started out as an ionosphere radar. So it's not simply a telescope, but it really is an incoherent scatter radar that was originally designed to study the ionosphere. So, Angel, thank you for coming, and please give us an update on Arecibo.
Well, thank you very much. I'll also thank everyone from HamSCI. Mi charla va a ser en español, espero esté bien con ustedes. Okay. Well, good morning, everyone. And again, thanks to Nathaniel and HamSCI for getting me down here too. And there's a couple people involved. Well, I'm going to be talking about Hurricane Maria, Puerto Rico, and the observatory. So there was a devastating hurricane last year that passed through Puerto Rico. So some of the topics we'll cover is just the impact of Hurricane Maria, some of the people responsible that helped out, and again the status. Where is HamSCI right now after the hurricane? So again, the HamSCI Observatory is an institution that started construction in 1959. In 1963, we started operations. It's still the world's largest operating telescope. Somebody has a phone call. Oh, that's your time. Oh, my time up already, Phil. I'll speak real quick. Okay, and so it's still the world's largest operating radio radar telescope. I mean, it is the world's largest radio radar telescope and the world's largest functioning radio telescope. We know there's that big telescope in China, the FAST telescope, but I do an analogy with the FAST telescope and HamSCI was, this is a much larger telescope. Actually, the working aperture is about the same, but it's like comparing those old rotary phones they came sometimes with these touch tones. It's a big phone, and then you have an iPhone right next to it. That big phone it's big, but it only does one thing. So an HamSCI is multifaceted. So they're not going to have any transmitters. They don't have transmitters. We have two transmitters. So that's why we do radio astronomy out of Earth Sciences and planetary radar. We also have a big visitor center. Okay, so we prepare, before these hurricanes, we try to prepare the observatory. As you see someone hanging from the line feed, that's the 430 line feed that's suspended 500 feet in the air. Yeah, see. Yeah, there's somebody hanging from the line feed there. And so what we do actually is just remove the bottom 10 feet of this 96-foot long line feed. You can see the guy, there's a dish underneath there. So we try. So apart from that, then what we do, we stow the drive systems, the dome, what we call the carriage house, where this is housed, and the azimuth arm. We try to put it, perpendicular to the wing. So just to minimize, again, there's not a lot of wind resistance, with the exception of the dome. So again, we just process, the basic steps that we do, the basic SOPs, just the pre-season preparations here. We track the storm as far as we can, and then the preparations shut down. Make sure everyone we do the work, get the site ready, but we have people that have families, so we want to get the site ready and make sure everyone goes home and prepares their own homes as well. Okay, interesting that last year in Puerto Rico, we had record rainfall before Hurricane Maria. Okay, before Hurricane Maria, we had record rainfall in the first and second quarters of 2017. And then Hurricane Irma came about 2 weeks early. And luckily, Hurricane Irma passed to the north, a little bit to the north. Our neighboring islands in Culebra, where Ethan Miller has a site, and we have a remote operating facility there. It hit those island municipalities a little bit hard, and a little bit north coast, but it didn't miss us. But with that, we were out for about a week without electricity there, and that didn't touch really the island. And then came Hurricane Maria on September 20th. Category 4 hurricane entered the island in the southeast quadrant. You'll see a slide, and it exited right through HamSCI. So you see, pretty big hurricane. You see that coming. There's where it entered here. It was pretty when we were tracking it. Obviously, It's more impressive when you kind of look at it like this than when you're there. But it was very, very unnerving, to say the least, for everyone at the observatory, everyone on the island. So we had maximum winds of 155 miles an hour, measured at the observatory, 180 to 128 miles per hour at the observatory measured. We had 35 inches of rain in 24 hours. A lot. A lot, I tell you. It's a lot of rain. It's a lot of rain. So not only that, it took 12 hours to cross the island. I mean, it took 12 hours, and it's incredible that. Let me show you this next slide here. But the impact. Okay, so when it crossed the island, the impact to Puerto Rico, we lost 100% of power. The whole island lost power. Okay, no potable water for 90% of the island. Okay, and then communications have gone. No communications. Okay, the cell, landlines, and internet. And obviously, then you had shortages of fuel. I remember waiting in line 10 hours for $10 of gasoline. And then, because it was rationed, so I guess they eliminated the ration, because if I get $10 today, I gotta go back tomorrow, because by the time I get to the line, the front of the line, oh man, that $10 I wasted is gone. So then they eliminated that problem. And then there's no cash, because no ATMs weren't working. And there was no food, supplies were not available. There's nothing in, no stores, because people that own stores also have homes and families, so they were not going. So there goes Hurricane Maria coming through the bottom southeast section of the island. And Arecibo Observatory is like right there, and exited Arecibo. You see there, and you see the plot on the right, it's a wind plot. You see time versus miles per hour. You see how it comes up. This is the beginning of the hurricane, and that's the eye. That is the eye of the hurricane. And that's the backside of the hurricane, and there's the barometric pressure. And it was interesting, neighbors, I remember neighbors that during the eye, they started to take panels and stuff down, because it looks like a beautiful sunny day in the Caribbean. It's just fantastic, beautiful. And then obviously, they say, don't take that down. And you see what happened on the other side. So there's some of the damage. Okay, most of you have seen the pictures of the observatory. There is the line feed, the 430 line feed. That line feed used to be about down to here. It's hanging from some of the guys, and that used to be 96 feet long. So you see it. Took a picture. Just this is the day right after. So it was still hanging, and you see here, that hole is not. It wasn't caused by the hurricane. That's just a hole in the center of the dish to hoist things up to the platform. It's just a picture. You can see how the water is at the bottom of the dish. More than we have a 12-meter reference antenna. Some of the panels blew off of there. This is you guys have seen it. This is the catwalk. This is the underneath the underside of the catwalk. Some of the panels from the catwalk also fell on top of the dish. So heavy winds. You can see some of the damage caused by. There's a piece of the line feed there where it went through the dish. There's another piece of the line feed right there on the dish. And some of the antennas, our HF antennas designed by my good friend Jim Breakoff, right in front here. And here's Jim. There's one of your dipoles there. And so you see, that was for you, Jim. And so you can see the water underneath. So where the pieces of the catwalk fell through, pieces of the line feed fell through. It was very, very devastating. And you guys have seen that. Oops. Our point has stopped working. Yeah, it's a little sound thing. Oh, now I can see what I'm doing. going to. Before Phil's alarm goes off again. Okay. All right. So yeah, we'll try one quick here. 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 Okay, there. It's just pictures of the devastation at the observatory. You see, there's a piece of the line feed right there hanging. There's a piece of the line feed hanging. There's some of the buildings that were affected too. Jim, you probably remember that. That's the Jodie Foster building in Contact. That's where she stays. It's a little bit different from the movies. But you see, there's another unit right here. That's a part of the roof there. So we'll try to go a little bit quick here. So there's one of the photometers. And there's the devastation. Every single road looked like that. So damage summary of what happened. So the 430 line feed was destroyed, okay? And then what happens when the pieces of the line feed fell down and the catwalk fell down, and you had pieces of the primary reflector that they were ruined. But those are replaceable panels, and like 39,000 of these 3x6 foot panels. That has been replaced. We had multiple leaks on the roof. Coax broken for the HF facility. We had 3-inch air core coax. That was broken, but that's been replaced as well. The laser rangers, we have laser rangers that measure the height of the platform. That was gone. And obviously severe flooding. And Hurricane Maria passed through my house. Here, let's see if we can play a couple of seconds of this. That's a neighbor's house right there. You can see I was filming it because it was coming from the south to the north, and the winds at this time. There's a friend's house across the street there. The winds there were about 120 miles an hour. That was me trying to. So it came down. Stop that there. And then luckily, the first thing I wanted to look at. So I had my friend's cars in my lot there. The first thing I wanted to look at was my antenna. So my antenna survived. So that's a Skyhawk. They're designed also by Jim. So that Jim. And really enabled IHF contact there, so it was very good. Thank you a lot, Jim, for designing that antenna. So again, ham radio was very crucial. We had an amazing network of friends that answered. On the first call I got on 260, and it looks like that N3 Mike Victor Fox was amazing. He got on. He put me on the cluster. As soon as I got on the cluster, then I got all these friends that came on. Friends like Jim, Joan Taylor came on, Hal Kraft, the vice president of Cornell. So I had this amazing friends here. And we also had these guys that helped, okay? We had V2AED, KM6FOH, Chip, who's receiving the technical award this time in Dayton this year. And these guys were the real heroes. Please, ladies and gentlemen, I want these people to stand up. These are the heroes. How these guys work. Really, these guys are the real heroes. Thank you so much for that. So anyway, I know I don't have a lot of time here. So anyway, WWROF also donated a lot of generators to Puerto Rico. The YASME group with the repeaters and food, batteries. These guys sent down food, batteries, radios, chainsaws. They did everything. These guys are the real heroes. I couldn't have done anything without these guys. These guys are really good. Thank you. That was ham radio, and the observatory. The first contact that the observatory was alive was the next day when I went up there behind it. It usually takes me 10 minutes to get up to the observatory. It took me 2.5 hours behind a backhoe. I went up there and then we made contact, and that was amazing. These guys, and then we had a visit from FEMA and Red Cross. This young lady is the ham of the year. valve MV9L. So they brought stuff in, and we distributed it to a lot of people. We had, these guys will sit down a lot of food. So then we had so much food, we just give it out to nursing homes and abused children homes with my XYL right there. So, okay, operations and challenges after Arecibo. So again, we got to focus, okay, just getting, focusing on getting all the staff back together, the debris, the power, we had no commercial power. Power came back to the observatory around December. Okay, so we couldn't do anything. We couldn't do but we couldn't do planetary radar because we need external power. We have 4 1-megawatt generators that using it all this time. The cores went out, so we had to recore 3 generators. So we did start observing 7 days after the hurricane. 7 days after hurricane in transit mode. Transit mode, we just moved the telescope and just let the sky drift over. So we did do science, but so there was a lot of challenges after Maria. But luckily, with the incredible staff we had, we were observing in 7 days. So the recovery. So we established communications there via ham radio. 55% of the staff arrived here. The roads, everything were clear. Commercial power would again restored in 2000 in December. And in January, 100% of the, well, not 100% of the operations excluding, so it's not 100% because we can't do planetary radar yet because we're still waiting for the repair of this generators. So again, we were lucky. We got some funding from Congress. We had $14.3 million for repairs. So that was fantastic on their part. We're still waiting for the monies. But again, hurricane season starts again in 2 weeks. So 2 weeks. So we have to still perform all those repairs. We got to get the generators fixed. We got to get the line feed and with the money. And we have to do again when everything fell on the dish. The dish used to be the RMS error across 1,000 feet was like 2 millimeters. We don't know what it is right now. So we have to next week. There are going to be some people arriving to check that the panel and calibrate that again. So I try to be quick. Sorry about that, Nathaniel. Thank you very much, ladies and gentlemen.
Bill comes back up.
Yeah, Jim.
You forgot about the spam.
Oh yeah, well yeah. Thanks to Chip, sent down like 300 pounds of spam. Wait, Chip, we've got a spam filter this year.
It was good, Ben.
Yes.
Hey, with being in the hurricane path and a lot of hurricanes, what was so special about Arecibo that the National Science Foundation selected that site to build that facility?
Okay, there's a couple of things. Okay, the geographical position of Arecibo. Okay, first of all, you see the dish. The dish is 1,000 feet across, about 300 feet deep. So you had to get a place with like a sinkhole. So it had to be someplace. So because you don't want to excavate a hole that big, it's a lot of trouble with it. What are you going to do with the dirt to take out? Yeah. So they've tried it so that there was a few areas in Puerto Rico, Hawaii, Cuba, and as well. So that was in like '59. So we know why they didn't take Cuba, and Hawaii was a little bit far away. And so logistically, Puerto Rico was best, and Arecibo was the best area. And I was born in Arecibo. It was good. And then any other questions? Yes.
You say that they have to recalibrate the site. What's involved in doing a recalibration?
Well, again, so we have to. But what I mean by calibration is we want to see how spherical the dish is. It's not a parabola; it's a sphere. So how I mentioned the last time we calibrated the dish, it was 2 millimeter RMS across 1,000 feet. So right now, with the shifting of the dirt, underneath the dish, because this is in a natural sinkhole, so it's in the karst mountains. It's karst mountain area, and so we we have to recalibrate that. So how we did it last time was we put reflectors on the 39,000 panels, use the lights, but now we're going to use lasers to do this. Next week we're going to start this calibration process.
Okay, last question.
Where?
Oh, you're just
Okay, he's good.
Okay, thank you very much.
Thank you very much again.
Really appreciate it. Sorry. And he's now going to be presenting work about sporadic E and weather systems. And this is actually work done by Joseph Zekovich, Kilo 1 Yankee Oscar Whiskey.
Yes. I'm really honored to follow him. That's actually quite a privilege to me. And Puerto Rico Silovanto.
Gracias.
Yes. I forgot to wear my T-shirt, which basically means Puerto Rico will rise again. Okay? So, and this community was truly incredible. And I had a lot of worries about my friends down at Arecibo, and that man right over there is one of the people who made me sleep at night. Because he was on the air all the time and with tremendous backup from Jen and Chip. That was an outstanding job. So, I'm going to switch gears a little bit, and I'm presenting this as an update on something that I presented last year, which is on behalf of my friend Joe Dukevich, who is an amateur in Harvard, Massachusetts, which is a little ways away from MIT Haystack Observatory where I do my work. And Joe is an extremely keen observer. Joe is a classic example of a citizen scientist who just wonders and says, that's funny, I don't know why that's happening. And this work actually led to a very nice QSD article in December, you look that up, that's generated a lot of information. And so Joe thought it would be useful to just very briefly update people on the fact that he's not done observing this. So, we're going to introduce this. I'm going to very briefly, for those of you who haven't read the article or weren't privileged enough to be here with us yet last year, recap what he had discovered. And then there's some new stuff in this winter. And anybody here on 6 meters for sporadic E in the last, yes, you'll notice that things are kicking up. And so there's some interesting conclusions that seem to reinforce what he figured out last year. So, this is Joe. He's a retired reliability engineering fellow from the Raytheon type of people in the greater Boston area. He's been licensed for a very long time. Has a very modest station, but he's really into propagation, and specifically 6 meters sporadic E. And then, I won't tell you about me, but that's me. So, and that happens to be where we are, which is in Joe's backyard. So one of the nice things is that Joe started this investigation all on his own, okay, and then came to me and HamSCI and a couple people and said, is there anything interesting in here for you? And our eyebrows went up. And we've been talking to him ever since, and in fact have connected to the international community. There's some meteorologists in the UK who have latched onto this. So what did he figure out? Obviously, those of you who try to use sporadic E for things like 6 meter skip, there's a lot of variables. It's not random, okay, and the scientific community agrees with that. It's just that we can't predict it yet. And no, there's, according to somebody, there are known knowns, known unknowns, and unknown unknowns. And so I won't go farther than that. But the key thing that Joe observed and then later connected with other people who have been pursuing this professionally is that things in the lower atmosphere appear to be affecting things in the upper atmosphere. Specifically, there is a very tight correlation between upper-level, low-pressure systems of the kind that appear on your weather forecast and sporadic E. And one of the main theories for sporadic E is that there is a severe wind shear at the E region at about 100 kilometers, where suddenly within a kilometer or two, the ionosphere flips direction. That creates little ledges in electron density. These very, very sharp gradients are things that will then forward reflect as and create sporadic E. These are very, very localized things. You can have a spot where it works and a spot where it doesn't. So amateur radio is a perfect way to see and document these occurrences. He also discovered, sadly, that if you want to be in ESville, don't necessarily live in North America statistically. He also figured out that he has a theory about how maybe there's a magnetic field strength effect that's also affecting that. The jury's still out on that. We're trying to figure out whether that's the case. But he does notice that multi-hop sporadic E over the North Atlantic, so from North America to EU, seems to only happen when there are large storm systems present and positioned properly to create reflection layers. But then the further south we go, there seems to be a less of a correlation on storms. So maybe there's lots of other factors that you could read in here. So obviously this is the beginning of an investigation. This is, by the way, some statistics from a 2008 paper by Christina Ross, who is a German researcher for as part of her doctorate. This is just statistical averages of the occurrence of sporadic E in winter, spring, summer, and fall of 2008. And if you look very carefully here, of course, you'll notice that North America is not entirely the place to be sporadic E compared to things like Europe. I mean, there's still a hole in summer. What really got his attention was these two Atlantic storms on June 13th, 2016. There was a nice upper low right here off the Canadian Maritimes, and then another low that hung out over Europe. And there's the X at the same time. So in fact, he noticed this and asked the classic question, that's funny, I wonder why that is happening. Here's another view. There's New England, there's one of the upper lows, there's the second upper low. And so the idea was that sporadic E is very nicely forming where those two storms are. This is, and what he figured out when he connected with the HamSCI community is lower to upper atmosphere coupling is absolutely at the edge of our field. And it's a topic that showed up maybe only in the last decade. So independently, he's confirming that there are whole atmosphere coupling things that we have to honestly take into account, and that this data is very interesting from that point of view. So he conducted that last summer, wrote the QSD article up, and then, like Joe, being a clever person, he kept it forever. This is a little bit of an update. This is what he figured out. In the winter season, there is a winter sporadic E season. It's just usually much weaker statistically, and so there's a bit of the, it's too crowded, nobody goes there anymore effect, in that people don't always look for it. But there were some very nice winter ES openings in December and January to show what could possibly cause this. We had low sun angles, low exposure, so from what I said earlier, low production of, for example, E region ionospheric density. We are absolutely at the bottom of the solar cycle. I don't think I can tell this from that. The temperatures were on average reasonably cold this past winter compared to other ones. And as we said, summer is usually statistically the hot season. That's why everybody from June is thinking about it. Look at that in December 13th, 2017. All of these paths suddenly opened up. Why do we know that? Things like the Whisper Network, things like the Reverse Beacon Network, which this community has created to check out what propagation looks like. So he noticed that, and there was the jet stream, December 13th, 2017. So, and by the way, there's the minimum temperature. So having sporadic E localized on these gradients seems to be holding up. So we theorize that there's actually a change in the amount of wave activity that's coming up from the lower atmosphere in neutral winds and then breaking in the ionosphere and transferring some of that energy to the atmosphere, medium sporadic E ledges. Here's another example from December 31st, 2017. Lots of paths open here, even some open here, and there was the jet stream right through there. And so, in fact, if I flipped back and forth, you can pretty well see that there are, in fact, some places where these low pressure systems here and here seem to be causing lots of interesting paths. Joe, being a completist, here's one more, January 4th, 2018. Notice why you started to pay attention yet again. So there's all of these paths to the Midwest from here to the East Coast, and where was the jet stream trough right there? By the way, this is why our winter was so unusual, with all of these jet stream changes this winter compared to other winters. But it's very nicely correlated with openings on 6-meter paths. Once again, 1845 later in that day. So these are, as he says, notice the trend. So the theory seems to be holding up that there is maybe a tendency for sporadic to form on strong jet stream boundaries. And he even makes some more of some of his observations to be verified by people who will sit there and try to model it. There is always a but, okay? So I mentioned in general, the jet stream tends to follow west to east in the overall pattern, but obviously there's always a but, and so you always have to find the null case, the thing that doesn't agree with the others. On January 13th and 14th, there was a very similar jet stream, but we didn't have ES openings. However, well, geez, we had a K5, geomagnetic storm, G1 class from NOAA, and that probably jumbled everything else up, and most of the 6-meter hams were staying on meteor scatter at that point, and they hadn't moved to FT8, so there's a bit of a May 7th, not that long ago, so this is the beginning of the season that I asked for hands about. Here's some paths open here. Here's the front. So things that are gradients that are happening in here seem to still be, and this particular gradient seems to be enhancing sporadic heat to the point where these paths are starting to be made, and a little while later, boom. So those of you who are paying attention to 6 meters, turn on your radios. There's some very interesting stuff, and there's pure science coming right out of this. And in fact, that cloud formed, the hot spot right here, formed in front of this fast-moving, basically frontal boundary. So we think that that's actually altering the wave activity that's propagating up from the lower atmosphere. So very briefly, his point is that winter sporadic heat does exist. It seems to be forming on jet stream boundaries, and 2018 seems to be starting similar to 2017 and 2016. On average, ES seems to be forming over the North Atlantic near these storm and frontal boundaries. And by the way, as we saw, summer sporadic heat can also form over land if the frontal boundaries are hanging out over the middle of the country or somewhere else appropriate. And so get on your radios for 10 meter and 6 meter sporadic heat, and HamSCI will be organizing itself to collect your observations in many different ways, and I think we can advance the science of sporadic heat. So that's just an update from Joe. I will be happy to take more tiny questions about what I know about it. So thanks. It's quite variable, and some of that also, the question is, what is the typical ES opening? Some of that is also depends on what direction you're looking in as well.
I think we probably got another 15 minutes. Yeah.
That there's not a one-to-one absolute correlation to the edge of the front. We think in a general area the wave activity is enhanced. But the real mystery is then which waves are actually forming up the shears and which ones are not. And they just come out and those of you in the audience can do that. What's your response? Hours. Just, right, so you can have things that are reasonably stable, and that's a different mystery that says that, hey, if there's transient wave activity, how do you get things happening for hours? So I think that, as in many things, there are multiple classes of phenomena here. They've all gotten the same label, but we're beginning to, I think, try to tease them apart. Yes. Go back the other way. Once again, I think there's multiple things that may be in play here. Daniel, how many? One more. Yeah. Why is 6 meters the benchmark? I'm going to go back to that Yogi Berra quote again. People tend to, because one of the other, those of you who operate 6 meters know that things can be absolutely quiet, absolutely nothing going on, and suddenly for a half an hour we almost have to turn the RF game down. Everything explodes, and then immediately it disappears. So I think its sporadic nature is so dramatic that I think people have gravitated to 6 meters just because it is not like a lot of the longer wavelengths.
But part of that isn't it part of it that the lower bands, they're going to be refracted by the
Yes.
by the other parts of the plasma?
That's also true. 50 megahertz, that's way above the local plasma frequency in the ionosphere, so the ray paths are definitely refracted much less at 50 megahertz than they would be at 10 meters, which is now I'm thinking about that. Anybody got a whiteboard? Don't get me started.
Thank you very much. This is going to be the last talk for the day, and this is a follow-up on something that happened last year. So last year we had this forum, and a number of us gave a talk about the total solar eclipse that is happening this past August. And so you can see I have quite a long co-author list here, and if you're on this co-author list, please raise your hand. So we've got Bill and Magda over there, Spencer, Bill, Josh back there, and there's a few others. And And this is because we did a solar eclipse QSO party that really involved the entire amateur radio community. And so really this list should be much longer than it is right now. We do have the HamSCI community there, so thank you very much. So, we had the solar eclipse QSO party last August 21st, and it took place 4 hours before the center time of the eclipse, and it goes to 4 hours after, so a total of 8 hours. And a few years ago, when I was in graduate school, I had met Magda, and she was planning on studying the solar eclipse with Greg Earl, and they were going to be doing it with professional sorts of instrumentation. And I saw that, I said, well, I've just started using reverse beacon network to look at ionospheric effects. And so I'm like, can we see those eclipse effects using the reverse beacon network and using a ham radio contest? And so they said, okay, let's try that. So we came up with the solar eclipse QSO party, and we tried to make this a science experiment that was as contest-like as possible. Because one of the motivations for that is we have contests that go on throughout the year, different weekends. So this is a source of data that we as HamSCI don't really need to do anything. We can just go use contest data to look at other days and other events. But this is a perfect case to say, okay, we have a controlled experiment essentially. We know when and where the eclipse is going to happen. Let's create a contest around that. So this contest like 2 points for CW or digital, because those are the ones that can be observed most easily by the automated systems like Reverse Beacon Network, PSK Reporter, WhisperNet. You get 1 point per phone, and we wanted to make people flood the entire spatial area under the eclipse with signals. So we wanted to multiply the score by the number of grid squares so that we could encourage people to talk to as many different areas as possible. And of course, they had to give their RST, and we asked for a 60-character grid square, if possible. And then we got our data sources from Reverse Beacon Network, PSK Reporter, WhisperNet, and also participants submitted logs, and they submitted those to hamsci.org. And so we received, we received about 600 logs. I was able to parse 570 of them, and of those, we had over 29,000 QSOs that I was able to count as valid, over 4,929 unique call signs, and almost 650 grid squares and 80 DX entities. So these are really good numbers. So we have great participation from the ham radio community. From the big three collecting facilities, we had globally over this 8-hour period over 600,000 RBN spots, over 600,000 WhisperNet spots, over 1.2 million PSK Reporter spots, as I said, over 29,000 log spots. So what does this all look like? Here it is. This is just the Reverse Beacon Network spots over the continental US, a little bit of Canada, and a little bit of Mexico, over the eclipse path area. And so what you're looking at, and I want you to count very carefully, there's 312,579 colored dots on here. Okay, so you can check that, count that later. Now, each of those dots are midpoints between a Reverse Beacon Network receiver, which is a star, and a ham radio transmitter, basically SEQP participant station, which are the little black dots. So on here there's 1,184 identified SEQP stations transmitting on CW, 49 stars, and then each of the colored dots is a RBN spot, and it's midway between the receiver and the transmitter. And the reason we picked midway is because we wanted to know what the ionosphere was doing. So midway is, we're assuming single hop propagation, and so we're assuming that's the reflection point, or the refraction point of that particular signal. And so this is color-coded by what I call obscuration factor, maximum obscuration factor. So if you have a 1 here, that means that total eclipse was experienced at that particular location. If you have a 0.5, that means that there was 50% of the area of the solar disk was covered by the lunar disk. So that's the color code here. So we had quite good coverage of the SEQP. Now, we've been working on this for quite some time, and this is kind of like a contest type of event. One thing we have not released yet are the actual winners of the contest, or the contest score. So we've had to work quite a bit to crunch through all that, because we had to write some of our own software to do logic checking and stuff. But here's the first reveal of the winners for the single operator category. So we have Red Trench, Alpha 3 Bravo, with a total score of 403,975 with 680 CWQSOs. We had K4BAI, John Laney with over 224,000 points, and W1SJ, Mitch Stern with over 180,000 points. Now, one other category that we actually included in here, and was we actually gave bonus points for being spotted by the Reverse Speaking Network by PSK Reporter. So that's one of the things that took so long with this scoring, is I had to get all of those spots from RBN and from PSK Reporter, and then Spencer over there and I, we worked together to do the scoring. And so we actually gave bonus points. So if you got spotted, that actually helped out your score. So congratulations to these top 3. And then for the multi-operator category, we have the E-Layer Contest Club, W0CC, which Ward is a participant in. And we have W0D and W5GAD. So congratulations. Ward Silver, the total score spreadsheet off to him yesterday, and so he's going to be posting that onto one of the contest websites or getting into a tabular form. So we will be posting the full score sheet soon, and when that happens, we'll make an announcement on HamSCI.org, so you can watch out for that. I also thought, well, we should give credit to the RBN operators. So a special thanks to Felipe Seglia and Pete Smith and Dick Williams and Alex Shavkopoulos and all the other operators of the RBN system, because that was the main data source for what I looked at. And also for these operators, this is what I call the 10,000 plus club. So these are the RBN receivers that spotted more than 10,000 spots throughout the SEQP period. So WE9D on the top there, far and away, with over 54,000 spots. So thank you very much. All right, so to actually do some science with this, I needed to reduce the data a bit. So I selected only the data with a 0.9 obscuration factor or greater and just looked at that. So now we have something that looks almost like just the total solar eclipse path. There's a little bit of partial eclipse on either side, but we started with that. And then I needed to plot the observations in a form that we could see what the effects are. So this is the main form. Every time you see a figure like this in the rest of this presentation, you'll know that the x and the y axes are the same. The color bar, that changes, but the x-axis and the y-axis, they remain the same. So on the y-axis, we have from 0 to 3,000 kilometers, and this is the midpoint distance between the transmitter and the receiver. And so for 14 megahertz, you can see that before the eclipse, most of the activity was between 1,000 and 2,000 kilometers range. And then over here, this axis here is epoch time relative to eclipse maximum. So I looked at the location of every single one of those points, figured out when the eclipse maximum was, and I placed it accordingly in the underlying data set that went into this. So back here, this is 1.5 hours before eclipse maximum. This is 1.5 hours after eclipse maximum. And then this curve over the top is the obscuration function for the center of the United States. So what we get out of this figure is that about up to 45 minutes before the eclipse started, we had a lot of activity on 20 meters. And the midpoint distance was between about 1,000 and 2,000 kilometers. Then, as the shadow comes by, the ionosphere weakens, we get more rays escaping into space, less refraction, the band starts shutting down. And then after the eclipse, starting about a half hour to 45 minutes after, you start seeing recovery as the ionosphere comes back up. So this is really nice, and this is pretty much what you would probably expect for 20 meters, like if you're going into the night, you'd see this sort of pattern. So this is very good. So I laid that out with 4 of the HF bands. So these are the 4 contest bands that we had good observations from, 28 megahertz and 21 megahertz, 10 and 15, the 10 meter band and the 15 meter band, they were, we didn't have much observations from there. But here's the 20 meter band, the 40 meter band, the 80 meter band, and the 160 meter band. So you can see that for the 40 meter band, we had fairly good propagation conditions the entire time. But during the eclipse, we started to see the band go long, kind of like you're going into that evening propagation. So it went long and then it came back in. And then on the lower bands, 80 and 160 meters, you started to see band openings during the eclipse where you didn't have communications before or after. So this is the summary plot of the RBN observations. Now, to get things into a referee journal, it's not enough to just, plot nice observations like this. This is very good, but we need to compare it to some sort of physics framework or some sort of theoretical framework and be able to explain some things. So to help with that, I contacted someone by the name of Joe Cuba at the Naval Research Laboratory, and he had written a paper where he predicted what the ionosphere would look like, what the electron densities would be given the eclipse. So he has a physics-based model called SAMI-3, and he was able to provide me with a prediction of the eclipse outputs. And then what I was able to do, and that's that's down here. So the colors that you see down here, this is electron density as a function of distance away from a transmitter. And then this is altitude up here, so we're going from 0 to 500 kilometers altitude. And then the colors back here are electron density along a 2D slice of the ionosphere. So this is from that model. So he gave me that, and he also gave me an uneclipsed version, which is plotted up here. And then I was able to contact another person by the name of Manny Cervera, and he has a program called FARLAP, which allows you to do ionospheric ray tracing. So if you put in electron densities, you can, and you tell it what frequency, so here we're using 14.03 megahertz, you're able to predict where a ray will land. And so using this, you can get an idea of what the path looks like. So our transmitter is AA2MF in Florida, and we're simulating it being received by WE9V in Wisconsin. Now, every time you see a red ray here, that means that the program predicts that a communication path is open between AA2MF and WE9V. When the red ray goes away, the path is shut down. So let's just take a look at this. I'll play this movie first. And so it starts off the same, but here now you're starting to see the eclipse over here. The electron densities go away, and then it comes back. And you can see how it changes between refracting off of the F region and sometimes refracting off of the E region. I think I need to move ahead because of time. So what we were able to do is I was able to take the RBN observations that I just showed you before. I made up simulated plots based on, we did that ray trace simulation between a whole grid of transmitters and the known locations of the RBN receivers. And that was Josh's job over there. He put that on the NJIT supercomputer and we ran all of the simulations. And so this is the whole thing here. Let's see if I have, let's flip to this one. So here's the simulation, here is the observations, but now this simulation is just for refractions less than 125 kilometers. So this is simulating things refracting off of the E region. And so we found that the E region refractions match best with the 20 meter band, but not with the lower bands. If we look at higher refractions, so the F region, greater than 125 kilometers altitude, we find that best agreement on the 40 and the 80 meter bands. And then 160 didn't show up. We think that's because the prediction actually had the electron density set a little bit too high, but if we had lowered those densities, we think we would have shown up there. But now, what this does is it gives us a way of comparing the two. And fortunately, so I was able to write all this up, and this has now been published in Geophysical Research Letters. It was just accepted last week, and it's now open access as of like 2 days ago. So if you go to HamSCI.org or even on ARRL.org, there's a news article about this. You can go find the link to this, and you can actually read the paper and you can see it ourselves. So in conclusion, we've generated over 2.5 million link soundings. We observed effects on all the different bands, and the ray tracing allowed us to figure out that the 20-meter signals most likely refracted off of the E region, while the lower bands most likely refracted off of the F region. And so now we're continuing to look at the data some more, look at finer scale structures, and try to learn some new things. So special thanks to many, many people that are listed here, all of you who participated in the American Radio Relay League for promoting this so well. So thank you very much.